it's a pleasure to have Samir Mathur talking about the secret structure of quantum gravity vacuum, please.
Thank you. It's a great pleasure to be here and to give the talk. So I want to share with you very abstract thoughts I've been having over the years about how we should think about quantum gravity and all the big puzzles that keep confusing me. So let's just begin somewhere with a list of things where semi-classical gravity works and where it has problems. So it does give a good description of gravitational waves, even fairly strong ones, as we have observed from the mergers of black holes. It also describes, for example, the structure of stars, where gravity is not too strong, even up to neutron stars. But we have also troubles. Of course, in black holes, as you know, you have the information paradox, and then you can use fuzzballs to solve that. There are other questions with black holes, like what happens to the matter in the star as the hole is evaporating? Where does all that go? What does the inside of the black hole mean? What happens to somebody who was sitting inside if a shell is falling on him? Is there really an interior to the black hole? And all these conceptual questions. And I will conjecture a model which I will give you towards the end of the talk, which explains what might be happening there. Okay? So that's the conjecture. But then we also have troubles with cosmology. We don't understand dark energy. And more recently, we seem to be facing a problem with what's called the Hubble tension. The Hubble constants values don't match between early and late times. And whatever we are learning from black holes suggests a possible way to think about resolving these problems as well. So the first thing to note is that both the black hole and cosmology involves the same physical scales. I'm sure most of you know that, but it's so important I just want to say it. So here's a black hole. You take a star or a ball of dust, it collapses, and as it goes through a critical radius, the light cones really turn inwards, and then everything must keep collapsing here, and so that radius is called the horizon. But the density at the point where you go through the horizon is still very low. That's why we have all the problems we have. We go through it at low density. But then if you look at expanding cosmology, this is a slice at any time, let's say t equal to t naught in cosmology, then you have expansion, and then you have the cosmological horizon, which is given by the radius h inverse. At that horizon, the light cones start pointing outwards, and if you use the Hubble equation, then you find just just elementary analysis of numbers, that the amount of mass which you have inside the cosmological horizon is just of the right order to make a black hole with radius equal to the cosmological horizon. So this density is the same as this density. So really the two problems are the same, it's just time reversed. Here you're sort of going inwards, you're going outwards. So there must be close connections between them, and you should definitely think of both things at the same time. And if you find there's some new physics which is required to resolve the black hole puzzles, and that's what I would like to believe, that there are corrections of order unity which you need to resolve black holes, then those same things might come and explain to us why things are going wrong at the cosmological horizon scale. All the issues with dark energy are at those scales and so on. And certainly in my thinking, whenever I'm thinking about something to do with fuzzballs and I make some crazy conjecture in the middle of the night, I immediately go and check if it is making sense here, because there's lots of data we have from cosmology. In fact, we live inside here. So we can go back and check if things are fitting with cosmology, and if it doesn't fit there, I discard the idea. Okay, so it's just good to keep them both in mind at the same time, just because of the length scales here. There are also several differences, but the similarities are also very close. So just to remind you what the Hubble tension problem is, if you look at measurements of local objects by looking at the redshifts, you get a certain value of h naught, and they have this plus or minus 1 or 2, I think. And if you look at the lambda CDM model and you use it to the cosmic microwave background, and so you get an extrapolation of what h naught should be, you get 67 plus or minus 2, and this is now a 4.5 sigma tension in there. So one of the solutions proposed to this is what's called early dark energy. So if you had an extra energy density of the order of 10% of the closure density at the time where radiation changed to dust, then it seems to resolve the tension. So just going back to the previous picture, if you had 10% of the energy in this region extra at the time that radiation changed to dust, it would resolve the Hubble tension. So you can see the kind of masses, scales, and energy densities we're talking about are the same as the scale of black hole energies, like 10% of the black hole energy and so on, it's an order unity correction to black hole physics. That's the kind of scales we are looking at. So just to tell you, the problems are very similar and why you should think of this problem at the same time as that problem. And okay, so it's the same scales. That's what we said here. And dark energy, of course, is 0.7 times the closure density. So again, that's 70% of the energy in the black hole of the radius in the cosmological horizon, all the words we said before. So again, if you're worrying about these questions, then it's also the same scales as black hole physics.
Samir, I just have a question on this statement that you made.
The previous page?
Yeah.
Yes.
Yeah, so you said that at the time of matter radiation equality, it has to be 10% more, right?
Yeah.
So does that mean that if the dark energy has decayed, if 10% of the dark matter has decayed to radiation, that would solve the problem?
If 10% of dark matter decayed to radiation at this time?
No. Suppose there's 10% more dark matter at that time,
Okay.
which has decayed to radiation. That
So
would solve
I don't think, what they need is something which is more like a cosmological constant. So with energy, with W equals -1, which lasts for a very short time. So something.
Yeah. So this, when you say 10% of energy closure density, it's more than that, you are saying.
Yeah, yeah.
It's not enough to have just 10% extra energy.
Yeah, it has to be in the form of a certain stress tensor, a form of an effective lambda. 10% energy density of closure density at that time. At that time, lambda is not doing much. It's too small. The normal lambda we have today. But a new kind of lambda, an effective lambda, which is 10% of the closure density at that time, which behaves like a lambda to leading order, so not like dark matter, which is like dust. But it should also decay quite quickly within 1 or 2 expansion time scales. This is rather a funny requirement. If it lasts longer than that, then it again contradicts something or the other.
Okay. Because Friedman equation is only sensitive to the total energy, right? Total energy density. It doesn't care about the lambda or...
No, only one of them is. The Hubble equation is, but the A double dot equation is not. So the
yeah, so that's the conservation of the energy momentum tensor, right?
Yeah, right. So the Friedman equation only knows the rho, but to know what rho will be at the next step, you need to know what is P. For the conservation. And so that you can take from the A double dot equation or from the equation of state.
Yeah.
But that's the P you require to be equal to minus rho for this extra dark energy thing to work.
Yeah, so I'm just wondering that if the matter just decayed, right, it seems that it would have the same effect because it just depletes the energy density. Right? Once it goes to radiation, it depletes much faster.
But it won't really go to acceleration, right? Because you need radiation is P equal, dust is P equal, W equals 0, radiation is W equals 1/3. But you need W equals -1. Okay, so I'm not sure that you effectively make W equals -1.
Okay.
But this is also just a model. There are people in astrophysics, everybody complains about everything. So there are people who also complain that this doesn't work. But it's still a very popular model. Okay, so anyway, this is just to talk about scales. But the overall lesson we are getting to is that the conventional picture is that of quantum gravity used to be that, at the Planck length, all kinds of hell breaks loose. But then once you get to longer length scales, everything is like smooth classical spacetime with small fluctuations. But the information puzzle in particular and all the other troubles also we are having tell us that what we need is a second mode of failure of the semi-classical approximation, not that curvature became Planck scale, but something else goes wrong when the curvature is nowhere near Planck scale, much more gentle. And so just to make it precise, how do you quantify what we need? So if you think of a curved spacetime like this, then you can think of the radius of curvature, that's I've called RC. And then you can talk of the distance over which that radius of curvature is maintained. So normally for a star, this L is much less than RC. So the star might be, let's say, 1,000, in some units, let's say 1,000 kilometers big, but then the radius of curvature there would be 1 million. So the length over which the curvature lasts is much smaller than the radius of curvature itself. And so that's sort of weak gravity. That's what the star is doing. While the case which you have, let's say, in the Hubble expansion cosmological horizon scale, or in this case of the black hole, is where the curvature radius is some RC, could be much bigger than Planck, not to do with Planck length, but the distance over which it lasts, L, is also of the order of RC or bigger. So somehow when you come to these situations, something new seems to be happening, which is not quite seen in these situations. And so whatever effect you're looking at cannot be expressed by a simple change in local Lagrangian, because if you add like an alpha prime r square, that's only small distance corrections. That's not what we are looking for. We're looking for something which changes things when the curvature could be low, but also lasts for a time which is long enough lasts for distance which is long enough to be of order the curvature, and that happens at the scale of the cosmological horizon, also happens at the black hole. Okay, so just to see where we should be going, let's just review a bit of simple history which all of you know very well. This was Bekenstein's problem. If you throw a box of gas into a black hole, the gas disappears, and then you can ask, have we reduced the entropy of the universe? That would look funny, but Bekenstein noticed the hole of course gets bigger, and then if you attribute an entropy of this much, he didn't have the constant, but if you are interested in entropy of this order, then you can save the second law of thermodynamics. Whatever you lose in the entropy of the matter, you get back from the entropy of the black hole. So that looks good, but then if you use a first law of thermodynamics, TdS equals dE, dE is the change in the mass of the black hole, and now you have attributed an entropy to the black hole, then the black hole seems to have a non-zero temperature. And then if you go back to thermodynamics, detailed balance tells you if black holes can absorb, they must also radiate. And so you again have a second paradox. And the puzzle was, in classical GR, black hole certainly absorbs, but then nothing can come out of the black hole in classical GR, so you're again contradicting the detailed balance of thermodynamics. So this is what Hawking was so worried about, but then of course we know the answer to this one, which Hawking solved. You essentially get, once you take quantum effects into account, the hole does radiate. And so let's go back and ask, these are the radiation particles that we talked about, Hawking radiation. So let's go back and ask, how did Hawking solve this puzzle? Where did these particles come from? Why couldn't Bekenstein see them, and why could Hawking see them? And the point is, these particles were already present as virtual fluctuations in the vacuum. If we did not know that the vacuum has virtual fluctuations, we wouldn't have known about these particles. And what happens is when you change the metric from, let's say, a dust ball to the metric of a black hole, the metric changes. The original metric had one set of vacuum fluctuations. The new shape of the metric has a different set of vacuum fluctuations, and the difference shows up as real particles. So that's basically what particle creation is. You go from one set of fluctuations being optimal to another set of fluctuations minimizing the energy, and the difference shows up as real particles. That's basically the Hawking effect. But you really have to understand virtual fluctuations, otherwise you would be stuck with this puzzle of violating thermodynamics. Well, now we are facing a different puzzle, because even with this we have saved thermodynamics, but the fact these two particle pairs are entangled is leading us to the information puzzle. Okay? So could it be that there is a set of virtual fluctuations that we have missed? Virtual fluctuations are easy to miss, and if you can find another set of fluctuations you have missed, then perhaps that's going to help us get the solution of the puzzle. So of course we know there are real electron-positron pairs in the lab, and what virtual fluctuations tell us, that we also have virtual fluctuations of E plus E minus pairs, and they are the ones which, for example, become Hawking radiation, and you can convert the virtual ones to real ones, and that's the dynamics of Hawking pair creation. So whenever I draw virtual particles, I just draw them slightly less dark, and so maybe you can think of those as virtual. So what could there be states that we could have missed? We certainly know that black holes should have a large number of microstates. That's all the way back from the time of Bekenstein. Of course, before this we didn't quite know perhaps what those microstates look like. But now that with all the work that we have of all the people here in the room and working on similar things, that the black hole things might be fuzzballs which are just geometrically drawn like this. The important thing is they are extended structures with a size which could be arbitrarily big. The more massive ones are even bigger. So the important thing is they are extended objects. And if they exist as real objects states in the theory, then there should be corresponding virtual fluctuations of these guys too. So obviously one should think about these, and one should think about what the vacuum is doing with these. And you might think that the really big structures like this are very heavy, so you should not think about them. The fluctuation will be small, but of course we also know that the entropy of Bekenstein is so large that the number of possible flavors of these is e to the s, and when you just put in rough estimates, it does look like you should consider them, because whatever suppression we expect from e to the minus action might be cancelled by the Raj degeneracy, which might be e to the plus s. Okay, so we just gave the name Vecro to this, which stands for virtual, because I am looking for fluctuations. The important thing is extended. They do have a size, and that's very important. They are compression resistant. If you've played with these kind of structures before, you'd notice that once you made a fuzzball, you try to compress it, doesn't want to compress or stretch. It's like any kind of molecule, like a benzene ring. So that will be important for something we'll talk about later, and O is just for objects. So I'll just use that for the virtual fluctuations of black holes. But this is going to be a key aspect of what I'm going to say here, that in the vacuum, if we had forgotten that there are virtual fluctuations of electron-positron pairs, we would not have found Hawking radiation and had the puzzle with thermodynamics and black holes. And now that we have this large number of virtual microstates of black holes, if we forget that there are corresponding virtual fluctuations of these, we might be making another mistake, and that might be responsible for all the difficulties we've been having. Okay, so this is what we call the Vector hypothesis. The vacuum has not only electron-positron pairs as virtual fluctuations, but also these virtual fluctuations of all sizes correspond to black hole microstates, and we've got to learn how to think about these. And the point is that these guys don't do much when you are in this situation where the curvature doesn't last for very long like a star, but they will do something important when you get to the black hole or to the scale of the cosmological horizon, and we just want to see why. So, okay, so let's play a little bit with virtual fluctuations to understand them. It just sounds so abstract. We don't quite know how to think about them. So let's just start with those which we know. So if we just take the normal fluctuations of a free scalar field or of gravitons, so these we know, nothing new about those. So if you take scalar fluctuations of a scalar field like this in an expanding cosmology, then any particular Fourier mode of a scalar field, it stretches under cosmological expansion. It gives pair creation of the scalar field. This has been very well computed. It's the same effect as in the black hole pair creation, not just applied to the expanding cosmology. And it turns out this is what gives rise to the perturbations which are important in inflation. So everything which you see in the universe, the perturbations we see, out of which ultimately we are constructed, really started off as these virtual fluctuations, and then they froze because of the expansion, the same as the Hawking effect, and they became real perturbations, which became everything you see around in this room now. So certainly this is a very important effect, but it doesn't have a very big effect on cosmological expansion. The energy of these perturbations is 10 to the minus 10 of the rest of the energy, so it doesn't really matter very much. Our interest is in a slightly different kind of vacuum fluctuations, those of extended objects, because we said these vectors are extended in size, and let's see if there's something different about the virtual fluctuations of extended objects. So just for a moment, think about, let's say, a meson made of a quark-antiquark pair. A meson has a size of 10 to the minus 13 centimeters. So let's just take that to be a size we are interested in, and let's talk about that as a toy model for extended objects, just so that we can know how to think about the virtual fluctuations of black hole states when we finally come back to it. Okay, so let's talk about virtual fluctuations a little more. If you actually have an energy mc square, you can actually have a real particle of mass m, but suppose you're in the vacuum with E equals 0, you can still get these virtual fluctuations. That's what we've been saying, and when space-time deforms, they can become real particles. We said all that before. But now let's think of a real meson which has this kind of a size and a certain mass, made of quark-antiquark with a gluon flux tube. Is there something called a virtual fluctuation of a meson? Should the vacuum contain virtual fluctuations of mesons? If it does, then we already know there are virtual fluctuations of extended objects, and let's see if that makes any difference to how we should think about virtual objects, because then when we come to fuzzballs, we have extended objects which are huge. So let's just see what an extended object, what the extended part does for us. So again, just to be more comfortable with virtual fluctuations, it's nothing very novel. If you just have a pendulum, the classical configuration tells you should be at x equal to 0, but the fact the wave function actually wants to spread a little bit around that, well, that's the virtual fluctuation. So that's all there is to it. The kinetic term in the potential makes the wave function, which is drawn in black, spread in this harmonic oscillator potential, and so it doesn't all sit at x equal to 0, and any part which is here, in particular the part which is under the barrier, if you just want to call it something, you can call that the virtual fluctuation. So that's all it is. Any wave function doesn't want to be at the classical minimum, but the kinetic term of quantum mechanics just spreads you out into other configurations, and that's all that we mean when we say virtual fluctuation. So it's this spread of the wave function that we are after. Okay, so virtual fluctuation means the fluctuation. And so if you have a virtual fluctuation of bound state, what does that mean? It just means that you have a quark and antiquark, but the places where those extra fluctuations happen are correlated. They want to be at a certain distance because the potential between them, now they're not treating them as free particles, but as interacting particles. So how far they appear, and if one appears here, the other would like to appear close to it and not at some random position. Okay, so it just means that the potential, once you take the interaction into account, these fluctuations happen at correlated positions, and that's all we mean by a virtual fluctuation of extended object. So if this is what this particular room looks like, you have virtual fluctuations of mesons everywhere. If you make a picture of the quantum gravity vacuum on the QCD lattice, which I had on the previous thing, if you really look carefully here, you should be able to see these correlations which correspond to the virtual mesons. But now if you just gradually expand the universe, this room is expanding at the Hubble expansion rate, well, nothing very dramatic happens because you just end up creating more space, but the density of virtual fluctuation remains the same, so you just end up creating more of these guys. So that's okay with everybody. You have to create more of these guys, so you just keep creating them. So if you expand very slowly, you just create more and more of these guys, but everything remains the same. It just looks like the normal vacuum. But now suppose the universe had a very rapid expansion where the Hubble rate was given by the gut scale. Now that's what happened during inflation, so let's just think about it. It's a purely artificial problem. We didn't really have a QCD vacuum at the guts inflation, but we're just thinking about a hypothetical problem, and so let's see what happens. So here I have my, I've drawn the meson here, I just drawn it a little bigger so you can see it. So this is my 10 to the minus 13 centimeters from here to here, but the cosmological horizon now at the gut scale was 10 to the minus 28 centimeters, so that I've drawn it here. So now you see that the two ends of this particular extended object lie outside the cosmological horizon, but the light cones there point outwards, and what does that actually mean? It means that if you have 2 points here and here, the proper distance between them has to keep increasing. That's what it means to be outside the horizon. Just like in a black hole, if you're inside the horizon, it means the thing has to come closer, it has to crush. But to be, if you have an anti-trap surface, if you're outside the cosmological horizon, it means the proper distance has to increase, otherwise you'll be violating the speed of light constraint. Okay. So this guy has to stretch, and so it will stretch and stretch, and you can see that's actually going to cost you some energy because there's a QCD string between here. So stretching of this bound object costs you some extra energy. So if I actually started you off in the QCD vacuum, and then I had suddenly started inflating at the gut scale, none of which is realistic, but suppose I did that, there'd be an extra energy which is coming from this stretching of the extended objects, which you wouldn't have thought about if you had just thought about fluctuations of independent massless scalars or whatever, or massive scalars, which are not extended objects. So that's the kind of effect we are looking for. And as we said, there are not many mesons at the gut scale, and that's not what we want to think about. But was there a question, please?
That's me. Okay, start doing.
Yeah, so the QCD string will break, right, if you try to stretch it?
It will break, but before it breaks, I think there is some extra energy anyway. You first stretch for a while, then you create more pairs, but all that it leads to extra energy.
Okay, but once it stretches beyond the QCD scale, it will start breaking.
It will start breaking, yeah. But there's still an extra energy till the point it breaks, because it has to put extra energy of 1 QQ bar pair before it can break.
Okay.
Yeah.
It looks like you're saying that the radius of curvature of the geometry is larger than the QCD string tension. So why aren't you in the deconfined phase?
Oh, absolutely. I mean, that's why I was saying this is all complete nonsense.
There are no strings, there are no mesons, there's a
all that is true.
gas.
I was saying that when if you're expanding, inflating at the gut scale, you really don't have the QCD vacuum there. I already said that. So this is just a toy model. Just think of something where you can have, which can stretch. It's not realistic to have QCD. You don't have guts, you don't have gluons, you don't have quarks. You're at the gut scale. It's all nonsense. We already said that. It's just to help us understand if you have extended objects and they cost you energy to extend, there'll be an extra energy when you are inflating, which you wouldn't get if you only had separate point-like objects, which cost you nothing to stretch. Everything else is wrong.
That energy is much, much less than the inflation scale. So it's small perturbation.
And that's fine. It could be. In this case, for sure. We're going to now apply to, we're just trying to guess what might happen, because certainly there aren't any mesons at the gut scale, and this is not what we want to do. But just like we talked about this meson, we can talk about bigger objects like benzene rings, which will have the same problem. Benzene ring would try to stretch, and then at some point it will break. But before it breaks, it will stretch and it will cost you extra energy. If we started inflating with the cosmological horizon, which was smaller than the benzene ring, which would also happen at the gut scale, except there were no benzene rings in the vacuum at the gut scale, at least ignorable amount of benzene rings. But again, if you talk about benzene rings, you would say, hey, the probability of having it is so small because it's so heavy, and you could say that also for a fuzzball, except the entropy factor here is very big, and we were arguing that's why we still may need to think about these guys. So the point would be, if you have these guys, which we called vectors, and if they are at your cosmological horizon scale, let's say whatever the horizon scale might be, and you start stretching, if you take a vector of radius the cosmological horizon, and you stretch it, let's say, to 1.5 times that size, the natural energy scale you put in from all that we know about black holes, we'll just make our first guess, would be of the order of a black hole energy of radius, of the black hole of that radius. And that's where we are saying an extra energy may come from, which you wouldn't see in any low energy processes in the universe, because you never end up stretching anything else fast enough like that. So the stretching of these virtual things, we are going to argue, can change physics in the cases when I was saying that you don't see gravity actually reproducing what we want, while in all the other cases, it won't create any significant effects. So so the idea would be that these virtual fluctuations are the ones we had missed, and they will close the gap between where GR seems to be working, semi-classical GR, and where there was a question back there for me.
Yeah, so normally if you have a bound system, it doesn't get stretched to the expansion of the universe, right?
So
Like the solar system doesn't get stretched.
So
as
yes and no. So what happens is the following. Let me go back to this slide. Yeah. So if you have a solar system, or if you even take the solar system, it is trying to stretch because of the expansion, but the attraction is trying to pull it in, and so it stabilizes to where it's just barely slightly more stretched than it would have been if there was no expansion, and nothing much happens. Okay. That's why I said, but if these two, the moment it becomes bigger and bigger compared to the size of the, how do I do that? That's amazing. Hey, can somebody help me? There's no cursor. Maybe I can just do it from here. No, that's just a cursor. This happened before also once, right? We couldn't.
Okay.
Yeah, just to play. Yeah, you should play from here. Yeah. Thank you.
Okay.
Thank you. Yeah, so let me answer the question. So that's why once this object starts becoming closer and closer to the cosmological horizon scale, it actually starts stretching more and more. For the same tension, it will actually stretch with it and not be, it will actually stretch a little bit. But the important thing is, once it becomes outside the cosmological horizon, it doesn't have a choice. It will keep stretching. So even if there's an attraction between them, you take two balls joined by an elastic band and you put them further out, separated than the cosmological horizon, there is no way it can prevent itself from stretching, because look at the structure of light cones. Even if you try to come inwards as much as possible at the speed of light, you will be at this edge of the light cone, and here will be at this edge of the light cone, and they are still going away from each other. That's the definition of a closed anti-trapped surface. So that's the extra physics we are putting in. The moment you get to a closed anti-trapped surface, things which don't want to stretch still have to stretch. And the same thing happens for a black hole. Things that don't normally want to compress, they are compression resistant. If you're inside a black hole, they have to compress because light cones point inwards. So we are saying whenever you get into these situations which have horizons, something new happens, because these virtual fluctuations react badly at that time. They don't react very badly anywhere else, and that's why we are okay in whatever else we are doing. But here something goes wrong, and that's why we're looking at these guys. Okay, so let's see where we were. Okay, so let's talk a little bit about the effects of vectors, get a little bit more familiar with this, because we want to then start using this stuff for something. So as we were saying, nothing much happens if you consider a star, because star creates a little bit of a dip in the potential, and each vector will stretch a little bit. But as Ashok was also saying, anything which doesn't want to stretch or compress, like a solar system or a molecule, we just compress a little bit or stretch a little bit and stabilize. And all the normal effects of vacuum deformation of vacuum fluctuation, which happen when you put any source in a theory, they all accounted for the low energy effective action. So all this stuff already goes into R root minus G and whatever you have. So it's not like I have to worry about the fact that the vacuum slightly shifts in character when I put a star. But when you have a black hole where the light cones point inwards, this compression, as I was just saying, is monotonic. This vector can't stop deforming because of the structure of light cones. And I'll come back and talk about black holes a little later. So I'm just drawing this schematically here and just moving on for now. But this is when the vectors can react badly. And so the picture of black hole formation is that normally vectors just stretch and remain virtual, except here the deformation of vector will be so big, they'll turn into actual on-shell fuzzball states. Now that's exactly what happened in Hawking radiation. If you make a small deformation of the metric in this room, the virtual particles are there, and their distribution slightly changes and relaxes to the new one. But if you change the metric enough to make a horizon, like Hawking did in his story of making a black hole, those same virtual fluctuations actually deform enough to become on-shell fluctuations. Okay? So we're just wondering that if the same thing can happen now, that these fluctuations, they normally just remain virtual objects, but in the cases where we do things like this, they're actually going to become on-shell. And we want to talk a little bit more about the details of how that should happen. But I wanted to first talk about cosmology and then come back to black holes. So let's just notice that in the cosmology, as we were saying, exactly the opposite happens. The vectors which have radii, if you have virtual fluctuation of this vector of the fuzzball, which is drawn in this dark thing here, anything which is larger than the cosmological horizon radius will be forced to stretch. Doesn't matter how much it doesn't want to stretch, it will be pulled apart. And the deformation of these guys, because they're elastic objects, will contribute an extra energy that we would normally not have thought about in cosmological expansion. What we're going to see now is that there are very strong constraints about when we should have extra energy in cosmology and when we should not. So let's see if any of that holds up. Okay. So anyway, just to get started on that story. Pardon?
We know that these cannot break.
No, we don't know that. And I'm sure they can break, just like we were talking about mesons a second ago.
Yeah.
But before anything breaks, it has to absorb there'll be some elastic energy before it breaks.
Yeah.
And that's all. Okay. And we're just putting in a hypothesis. We don't know anything about these vectors very much, but the only length scale in the problem is that if you take a vector of length of radius RV, V just stands for the vector, and you stretch it by order unity, let's say to 1.2 times its size or 0.8 times its size, the energy of the stretching or compression will be of the order of a black hole of mass RV. We just put that in because that's the only length scale in the puzzle. If you ask me to justify that, I really don't have one. Okay. But then, if you deform it by a factor of 2 and it breaks, absolutely, we don't have any idea. We just want to know if we can get effects at the right scale which don't conflict with any data we have from cosmology or which we have from observations outside the black hole. If we can fix all our puzzles while keeping consistent with all the observations, for the moment I would be happy.
So
yes.
In the regime where the vectors are small, can you compute their contribution to the Casimir energy?
Okay, so like suppose you have a lab experiment you're saying with like say put two plates that are 1 centimeter apart and try to measure Casimir energy.
Yeah, what would be the estimate?
I think it's a good question, but I would think that normally everything is suppressed by the Planck scale unless you can do something to compress or stretch them a lot. So you see you're putting two plates, right? You want those plates to try to do something to the vector. If those plates were compressing the vector, for example, by a factor of order 1, you would get a lot of energy from it. But if you don't do that, if you only fluctuate the vector by a small amount, it's probably all absorbed in r root minus g. So it would simply be asking what is the effect of the gravity back reaction when you're computing Casimir energy, and I'm guessing that's small. It's just the energy density of Casimir energy divided by Planck energy density. I'm guessing that's the only thing which comes in.
Okay.
So I think the only thing is, since you are nowhere near a horizon, nobody's forcing this guy to stretch or compress. Only horizons that force you to stretch and compress. And if you haven't gotten into that scale, I don't think they do anything. Is a question for me?
Yeah. So, but it seems like you're thinking about this as some exotic form of matter. Is that correct?
Yeah, there's just configurations of the theory. So they are as much of a matter configuration. A black hole configuration or a fuzzball is as much matter as a meson. So exactly.
Okay, so it's some stress energy, and what equation of state does it need to have all of the properties that you want?
I have no idea if it's the equation of state. We are just guessing its scale of energy because we know only one scale from the black hole. Then equation of state for this is something we would love to have. So in fact, the kind of work we are doing right now with my student Mathur is that we are trying to guess at various equations of state, knowing everything we know about black holes, and trying to fit it to the data with cosmology. And we don't have a good equation of state. I'll tell you what we get so far. But I think that's exactly the question, right? You'd like to know how these guys behave. In virtual fluctuation field theory, you know what to do with because you can compute Feynman diagrams. Here we don't even know the actual on-shell fuzzball states properly, right? We're just making a few of them now. It's just that we know these guys must be there because otherwise we have the information puzzle if they're not like extended objects and they don't have horizons. So we know these guys must be there and how many of them must be there, and everything else we have to guess to fit the picture together. And so we really are guessing.
So, Samir, I thought that Brandenburger said that W is equal to 1.
Pardon?
I thought that Brandenburger said that W is equal to 1 for the vectors.
Yeah, so Brandenburger actually wrote a paper last year or a year and a half ago where he put W equals 1 for these and solved for the both the cosmology and the black hole, and he got some interesting results. We can discuss that later. Yeah. So people have been trying different equations of state, and he had some justification for W equals 1, which comes from the black hole gas story. So okay, so he put a few things together, and we can talk about that. But yeah, people are just foundering here. I mean, we're just playing around to see what we can get. It's not like we have any answers. Okay. So in Minkowski space, so there's an important difference between this and cosmology, and the difference is the following. So what's the difference? So otherwise, you may think a black hole is just like cosmology, and we said that, but there is one important difference. In Minkowski space, you have these vector fluctuations of all sizes. There's no particular length scale. Once you go beyond Planck length, you can have 100 Planck lengths, a million miles, a trillion miles, anything is good. And you need to have the vectors at all scales because you have to solve the Hawking puzzle for a black hole of any size. You could make a black hole, a cylinder shell with a horizon radius of 3 kilometers or 3,000 kilometers or 3 million kilometers. The vectors of that size will compress and react and solve your puzzle. So you need the virtual fluctuations of all sizes, and that's what we had argued, that the more massive ones are more suppressed by action, but then they have a correspondingly bigger entropy, and those factors seem to be of the right order that they can cancel. But in cosmology, there is a constraint, because if you have an extended structure like a meson or a benzene ring or a vecro, that extended structure can't form unless light has had enough time to travel that distance in the history of the universe. So the energy of the universe might be lowered if you actually form a meson by binding the quark and the anti-quark, but if light hasn't had time to travel 10 to the minus 13 centimeters, then the vacuum hasn't settled down to a state where that bound state correlations exist. Okay, so this is the old causality problem, horizon problem, whatever you want to call it in cosmology, but that's certainly a condition we would like to put. And with that, let's see how the computations work out to estimate things. Let's take a flat cosmology whose metric is minus dt square, and then you have the expansion factor, and then you have the flat metric. And we'll take a power law expansion which goes as some a naught t to the alpha. So alpha is a number which will keep appearing on the slides now. And in terms of that, h is a dot over a, which is alpha over t. So that's where the alpha comes in. So alpha is 2/3 for dust and it's a half for radiation. And it's e to the t. So alpha is infinity if you are in the inflationary phase. So they are just different values of alpha. And the Hubble radius h inverse is just t over alpha. So that you can compute the distance that light has traveled since the Big Bang if you have an expansion of this kind, and it's t over 1 minus alpha. It's always like order t, but the exact constant depends on what alpha is. And we just said the vectors should have a size which is less than equal to the distance that light has been able to go. So we have a constraint that RV over the size of the cosmological horizon, it always has to be less than this number. Okay, that's just causality. So you can form vectors up to that radius, but not vectors which are bigger than that radius. And so let's look at some cases. So if you take the first case where you have alpha equals half in the radiation phase, I just copied that constraint equation again from the previous slide. If you put alpha equals to half, it tells you the radius of the vector is always going to be less than the radius of the cosmological horizon. So these guys are not forced to stretch. So the extra energy we were hoping to get from stretching, it doesn't have to happen here. Okay, this guy, if it's very stiff, it doesn't have to stretch. It may stretch a little bit, but it's not outside the horizon, it doesn't stretch. And actually that's a very good thing, because you don't want any extra energy in the radiation phase, because here the energy is very, very, very closely constrained by the Big Bang nucleosynthesis. So if we had added, let's say, another 20% of energy in that phase, it's already out. Okay, so it can accommodate at most half an extra neutrino with the margins of error, but if you put 20% more energy, you are gone. So you really didn't want any extra energy in that phase, and you can't get it at least from the stretching of vectors, because the vectors are never bigger than the cosmological horizon. But let's consider the case of dust domination now. So I put alpha equals 2/3, and then I find that all these vectors in this range can stretch. I put bigger than 1 because I want to be outside the horizon to stretch, but they can go all the way, RV can go all the way up to twice the cosmological horizon radius. We just put that number in alpha. So all the vectors in this region will be forced to stretch, and that gives you an extra energy. So there's some extra energy which is induced at the time that you actually go from the radiation phase to the dust phase. Now if you remember, that's exactly where we were hoping we might get something. So, and if you want to see how much is the energy, it's just some fraction of the closure energy density. We said we just put this in by hand sort of, but that was the only scale in the problem. If you compress a vector by order unity, you get an energy of the order of a black hole with that radius, but that's the same as the closure density. They're the same numbers we talked about at the start of the talk. And so then you find the following situation. You have a certain expansion rate when you have the horizon radius is growing at a certain rate, like 2t, when in the radiation phase, and then it changes over to 3/2 t when you enter the dust phase. Okay. And so what happens is here the vectors are smaller than the horizon, but here the vectors can be bigger than the horizon, and this is where the stretching starts. Okay. If the changeover was completely adiabatic, then actually you would have no extra energy, because the vectors could just settle down to the new configuration. If the changes are very sudden, you would get all this complete stretching by this factor of 2. So the actual power law should be something in between. And so you might expect you'll get some fraction of this closure energy density at that scale. And if you say, okay, you get 0.1 of the closure energy density from stretching of this vector, these are the same numbers we had before for the Hubble tension, repeating the Hubble tension story. So if you say that you get about 10% of the energy from the stretching of vectors, it's certainly coming in at the right time, because they need this energy, extra energy, exactly at the time, what's called T star, which is the time when you have radiation dust transition. And that's the time when we put this into our toy computer models. one thing which we find fairly universal in all the things that my student Mathur has been doing is that the extra burst of energy, you always end up getting it when you change the slope of the Hubble constant. Okay, so when you go from radiation to dust, you're going to get extra stuff. So let's see if we can get anything more than that. Yeah, please.
I think this is bringing it back to the first question I asked, that is it clear that the extra energy density that you are getting is in the form of cosmological constant?
So it is not completely clear, and we don't know that because we're still modeling the equation of state. But certainly whenever something comes from stretching something which is a brane, then you know it's always of the form of lambda. We don't know if this is the form of a brane, but if you stretch anything which has a constant tension, which I don't know about this guy, that is always lambda. So as you know, if you just stretch it, if you take a space filling D3 brane, it basically gives you from its stretching exactly lambda. So I don't know that this is exactly lambda. I don't even know whether the early dark energy has to be exactly lambda. And so those are things we don't know. All we are saying is the energy scale you can get is at the right time in the right order. But the actual equation of state, I'm blank on that.
And if you think of this as a gas of black holes, right, with some extra energy, that looks more like matter, that you can have some excess energy.
So it's not a gas of black holes in the sense that a gas of black hole with separate particles not joined which can separate. So that's the whole point here. This is an extended object. So the vector means that the whole object is extended and joined together, right? So all these models that you get, which you've been seeing of all these fuzzballs people have constructed, they are all linked together. It's more like a benzene ring. You can't pull them apart. It's not a bunch of dust sitting there. So that's very important for all this.
Yeah. But it doesn't seem to have a Lorentz invariant wall volume. Does it have a Lorentz invariant wall volume? That's what is needed for
Lorentz
cosmological
infinite
constant,
what?
right? Its wall volume of the
World volume.
yeah
Yeah.
doesn't have a Lorentz invariance, right?
Okay, so that is not clear from the picture I have drawn here. But the point is vacuum fluctuations don't look Lorentz invariant, but they are. So there is an interesting story about when people study vacuum fluctuation. Like if I give you a real meson in this room or a quark anti-quark pair or electron positron pair, it's not Lorentz invariant, it's at rest in some frame. But if you look at the virtual fluctuations of E plus E minus, they are Lorentz invariant. And the funny thing is they don't look Lorentz invariant because in any given frame when you try to write them, they look horribly non-Lorentz invariant. But there is some very nice work from the Tufts group where they actually checked how the Lorentz invariance comes out for things which are pair produced. And it's very subtle, but it works out beautifully. So I don't know how to show it for this guy because, you know, but if there are vacuum fluctuations, before any stretching is going on, when there's really Lorentz invariance, whatever the fluctuations are in the vacuum, they have to be Lorentz invariant. So that's by definition. Like if we just take 2B in the vacuum theory, it has whatever it is like Lorentz invariant. Just like mesons are extended objects, but their virtual fluctuations have to be Lorentz invariant. So it's not even a question.
Okay, so if you are thinking of this as vacuum fluctuation, can the energy density be negative? I mean, are you sure that it will be a positive energy density? Like fermionic vacuum fluctuations?
It could very well have been. For all that I
negative.
know right now, it could have been. Except, so it feeds into a much deeper question, which I would love to answer, but I'm still struggling with. How do you know that the cosmological constant is zero? Let's first address that question. Why is cosmological constant zero? Because once you know what it was for the starting configuration, then if you're stretching the vector, it costs you extra energy, that is clear. But you could ask, why was initially the thing zero? And that feeds directly into the cosmological constant puzzle. So you don't want to fine tune that away, like saying anthropic, I mean, that's horrible. So what you would really like to do is to say that in any configuration where the energy density wasn't zero, the universe starts expanding, but because these vectors soak up the energy by expansion, the vector configuration readjusts to dial the cosmological constant back to zero. If I could make that work, I would be very happy. Okay, I'm not satisfied that I can make that work, but I think this should be a way of soaking up any extra energy density in the vacuum because we have to tie into this other problem, why is lambda so close to zero? And that's always at the back of my mind when I'm playing with all these things. That's the one thing which we don't have a good answer for, but you can sort of see how it might work because if you have positive energy density, it expands, then you get a cosmological horizon, and all the vectors beyond that, they break because they stretch and they break. So the energy from the vectors depends on how much energy you had in the vacuum, and somehow I would love to fit that together to make sure that won't settle down to lambda equal to zero, but I haven't been able to do that. Okay. So I don't have a good answer for you on that. Okay, so anyway, let's just mention a couple of things. Not that we have any good answers for this, but then once you have passed through this stage of radiation to dust transition, you're in the dust phase, some part of this energy can get left over because the vectors which are bigger than the horizon, they are still stretched. And because they are stretched, they contribute energy, and then that causes more stretching. And so we put this in the computer and try to play with this. we try to see if you could like get into a phase where this extra energy is sort of self-consistent and gives you the dark energy today. It's still the right order. But what kept happening was we'd have something like dark energy for a while, then it would start going down. So after a few e-foldings, it went down. I was just very amused to see that recently the data they are getting from observations from DESI is suggesting that perhaps the lambda is not a constant. I'm sure all of you have heard about this. The W is not exactly -1 and it is slightly going down. But it's still going down much slower because these observations, if they are correct, and they may not be correct, it starts going down after about 8.5 e-folds. For us, it starts going down after about 3 e-folds. So, okay, it's not like we have anything very, very accurate there. But certainly if lambda was absolutely constant, we would have more trouble reproducing that because our lambda always starts going down after a while. The stretching of vectors after a while start to readjust and not stretch so much. So if lambda is actually going down in the real world, as the recent DESI observations suggest, I would be much happier. You can also try to see if that can help you get the energy for inflation, because the fact you introduce an inflaton field in the early universe just sounds very random to me. But so let's get back and see where did we get the extra energy from to at the transition from radiation to dust. And that came really, if you trace back to why it happened because the pressure dropped suddenly from the radiation phase to the dust phase. So whenever the pressure drops, the Hubble constant does what it does and you get this extra energy induced. But at the Guts scale, all the Guts particles freeze out, leaving only a few of the lower energy particles, so the pressure drops suddenly. So you again get stuck into this kind of phase. And again, whether you can maintain that expansion, I don't know. But you certainly get an extra burst of energy at the Guts scale when those particles freeze out, and so it goes from sort of radiation to sort of partially dust. And it may just be interesting to explore if that extra energy could trigger inflation, but we have even less information about this. Okay, so that's just things we are playing with. It's just interesting to see you get the right scales, but everything else is completely up in the air. So let me take my last few minutes and talk about black holes. So what's the question we want to answer? So you know that the Schwarzschild coordinates seem to give you a description which is valid outside the black hole, and the collapsing shell seems to just freeze at the horizon and you never see it going in. So many people would come back and ask you this question: if nothing ever falls into the black hole, am I not already self-consistent? I mean, haven't I solved the problem? Why do you worry about the inside? You must have heard that question now and then. And of course you get frustrated with that question because everybody who's studied gravity properly knows you can switch to Kruskal coordinates that seem to define the inside of the black hole, and then you can go inside the horizon, and that's why we actually have all our puzzles. So let's ask the question, is the inside of the black hole real? What is all this stuff? Everything looks so smooth here, you can hardly stop yourself from going in, like it looks like nothing special happens at the horizon. At the same time, do realize that in the CFT, the boundary CFT, the time that we have, we only have one time. We can't use different times like Kruskal time and Schwarzschild time. That time seems to describe more like the Schwarzschild time. It doesn't allow you to go inside the horizon. Somehow in the CFT, there's no analog of choosing arbitrary time slices inside. Okay? So maybe there is nothing other than the Schwarzschild time. And in that case, you have to explain what on earth is going on with switching over to Kruskal time and smoothly falling inside. And so that's the puzzle. Is all this real? What is this fake time? How come I can't see this time? As you guys know, this time already goes to infinity by the time this guy goes inside. So then, if whatever is doing inside, where is that in the CFT? I mean, can it ever be in the CFT? So all these questions are natural questions to ask. And so the question would be, let me just phrase the question a little more precisely. Suppose you have an observer sitting at the origin and a shell is coming in and it will go through its horizon here and then keep going in. How should we think of this observer sitting at the origin and the collapse of a shell? What's the full quantum gravity answer for that? Is there a CFT answer for that? Let's see if we can address that question. There was a question for me.
Can you comment on the proposition that the interior time is identified with modular time on the CFT side?
Okay, so the modular time is still the Schwarzschild time. I mean, the modular Hamiltonian which you make for this guy, that is the Schwarzschild Hamiltonian. The modular time is the Rindler time. So the Rindler time is the same as the Schwarzschild time. So the modular won't help me to go in. It's exactly the opposite.
Yeah, I got the impression that some people think that the modular time is helpful, but okay, you're saying it's...
Okay, maybe we can discuss. I would love to know what it is. Yeah, there could be very well something I didn't understand. Okay, so the question is clear, right? We just want to describe what happens to a guy sitting in and a shell is coming. If the shell goes to the horizon, this guy will still live for some time because it can only move at the speed of light. So there may be a few hours of time between here and here. Somebody mentioned the number of hours. I think Joseph mentioned how many hours you can live between the time from here to here. And in all the time, what is this person drinking coffee doing? Is she still drinking coffee? Or did she stop drinking coffee when the thing crossed the horizon? That's the question we are asking. Pardon? Tunneling into chocolate. Chocolate. Yeah, okay, tunneling chocolate. That's the answer. It's tunneling chocolate. Okay, we'll do that. Yeah. Okay, so let's go and remind ourselves of the story that we've thought about. As Yosef mentioned, we just want to study the story of tunneling and see what goes wrong. So it's a story of what goes wrong with the classical picture of collapse, where a star goes through its horizon, then the light cones turn inwards, and now nothing can come out, and you're stuck. But what you really hope is that a collapsing star actually goes instead into these fuzzballs. And so what you find is there's small property for tunneling from here to here, and then because the number of states is so large, the smallness of the tunneling can be offset by the degeneracy. And so instead of actually following the classical evolution that you expected here, the thing actually tunnels in a time of order unity and sort of ends up here. So that was a rough estimate, and there were more rough estimates after that. But what we've been doing recently is trying to make that more precise, and I'll talk about some aspects of that. So the quantum mechanical analogy was that if you take a quantum in a box and this is the box, if there are many, many surrounding boxes into which you can tunnel with a small amplitude of, let's say, 0.1, but the number of boxes is 100, then probability is 0.01, and so with 100 boxes, in a time of order unity, the particle will just vanish. Right? So that was the idea. If you have a small tunneling probability to something, and then in this case, there's an indirect argument that even indicates the two smallness and the bigness actually cancel each other using a cross-Hibble-Check relation. And a beautiful actual explicit calculation of this was done in a particular case by these people. So really we had some idea that this is a direction to pursue, but what we really like to ask is, okay, it's fair to say the wave function in a box will tunnel out, everybody knows that, but if the wave function in the box was a person drinking coffee, what does the person drinking coffee feel? It's a good question to ask, right? Yeah, 10 minutes, I'll be done. Okay, so let's go to something as simple as alpha decay. So this is the potential for alpha decay. This is the alpha nucleus inside, and there's a potential barrier. And so this is bouncing back and forth in this well, and so you can think of that as a clock. Okay. Now, suppose you didn't know about a tunneling and you thought the potential was just going up, 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 like this potential. This is almost the same wave function, right? So tunneling doesn't really affect the clock very much. And so let's really see what happens. We know this if the tunneling time is, let's say, 1 hour, alpha decay for something might be 1 hour. Some part of the wave function will go out, but the part which is bouncing back and forth here will still look like a normal clock. It's like the same period. Still looks like a normal clock. So how should we think about this? So what really happens is that in the beginning you just have a normal clock, so all the wave functions in this region. After some time the wave function is half here and half here, and after even more time there's very little here and most of the wave functions here. So we know all this. And so if you want to think about this clock, it's not like the clock got deformed or crushed or broken or something bad happened to it. It's the clock sort of faded away like the Cheshire cat. Okay? So it's not that the clock gets deformed or attacked in any way. All that happens is that the probability of having that clock sort of goes down. And let's see if we can use this logic to explain what happened to the inside of the black hole. And even though I'm just drawing pictures here, I'll show you how we get support from this picture from the dual CFT. Okay, so we'll match it both in the gravity picture where we are conjecturing and in the CFT. So let's come closer to gravity. That was just alpha decay. So there if you take a bubble of nothing, which is sort of, just something which happens, just tell you what a bubble of nothing is. If you have space-time with one compact circle, then that's like being in some minimum of the potential. These fluctuations here are just the small fluctuations of space-time, the semi-classical fluctuations of this room. So those are these fluctuations that you live here. But you can go off-shell by compressing the circle a little bit. That means you're going into this barrier region because it's pretty expensive to squeeze this. But there can be a virtual fluctuation squeezing it. It can then pinch off, which is still very expensive. You're still under the barrier. But if you squeeze it and even more and like really separate them a lot, you are out of the barrier again. And so that's the tunneling. Okay, so this is a series of configurations. It's exactly like the previous problem of alpha decay, but that's the nucleation of a bubble. And now you can see what would happen in this case. It's a very explicit problem. Suppose you put a quantum at the center of this room, and there's an extra circle. You can solve the problem of what's going to happen, or at least imagine what will happen if this little graviton sitting here. What will happen to the graviton as a bubble of nothing forms. So you can always change the size of the compact dimension to be such that the bubble forms in time 1 hour. And the bubble, when it forms, has a radius of 1 kilometer. Okay, so we just choose the size of that compact circle to be 1 million Planck lengths, and we'll get those numbers. Okay, so let's do that, and then we have something. So for that 1 hour, when the bubble will form, what will I see? The graviton will be here in the beginning, happy. It'll stay like here. The graviton in this room will always feel like it's the graviton in this room. It's just that the probability of the graviton being here is slowly going down, but the graviton doesn't know that. It's actually showing up outside. So it's something you can actually calculate. Whatever we said for alpha decay, everything is true here. I just drew the pictures. So this girl with coffee is slowly fading away. You can hardly see her here, but I did put her there. It's not showing up on the slide, but it's just getting dimmer and dimmer, and more of this girl with coffee is getting incorporated into this as little brown stuff in the coffee, which is exactly what Yosef had said in some words, I think. And so in the end, you only have the shell, which also contains, if it was just no coffee, they just had the bubble of nothing. It's a bubble of nothing decorated with some shards of coffee, and the girl is completely gone. Right? So this is very explicit in the sense that, you know, if you really wanted, you could do this, I suppose, not with a girl, but with a graviton. But let's see if we get some support for this from the dual CFT picture. So I'll be done in 5 minutes. So in the dual CFT, let's see how it works. So for people familiar with the D135 CFT, let me just assume that you can describe the ADS vacuum, which is drawn on the gravity side here, as just a lot of single circles, N1, N5 single circles, and let's say we throw a graviton into this. What happens then? The graviton, when it reaches the ADS region and falls in the CFT description, breaks into one left and one right mover. As they separate more and more, traveling at a speed of light on the circle, the graviton is going deeper and deeper down. And when they come around back and they meet again, the graviton has gone down and come all the way back up. And you can compute the time of this travel of graviton going down and up, exactly the same as the time for this guy to go around and up. And then it can just come out. So these are very old calculations. So we understand what happens when you throw something in and take something out in a CFT. Well, let's send two particles into the ADS throat. That's not difficult. So I did one particle is here, one particle is here, and so two particles are going in, and then they both come out. Except if these particles were very heavy, like I drew them thick this time, so they had a lot of energy each, you would expect they shouldn't come back right out on bouncing, but instead they should make some kind of a black hole, which is really a fuzzball down here. How do I see that in the CFT? If I just look at the free orbifold CFT, these guys just go around and come back, these guys just go around and come back, this guy doesn't even know about this, and this guy doesn't know about this. So clearly, I have to introduce the interaction in the CFT because the free CFT is not really mirroring all of gravity. So let's put in the deformation away from the free CFT, and what the deformation operator does in this case is that it takes two copies of this strands and joins them into one copy. So anybody who's played with the CFT in this language would know that, but if you don't, it's okay. Just take the picture for the moment. And so what will happen is, as this guy is going down, what really happens is that you have two particles of energy, you send a graviton of energy omega. These two pieces were omega by 2 each, but then it twists with another copy and you get 4 gravitons of copy energy omega by 4 each, and so on. And this is the way what really happens as this guy is going down the throat. So we've been doing this kind of stuff with twisting for a while, but this is just the pictures I'm pulling out of these calculations we've been doing. And so now let's see what happens when you put two particles in. Each of them is actually breaking into more and more as it goes on. And then there's a very simple thing you can find, which was clear all the way back from the earliest times you were looking at it. It's a very, very simple observations. If you have enough energy in the two gravitons to fill up all these strings, okay, by the time you reach the bottom, you will reach the black hole threshold. So all the other parameters cancel out. The coupling, the radius of the circles, and everything in the moduli, everything cancel out. If you fill up all the strings, you will actually reach the black hole threshold. If you don't fill up all the strings, you're below the black hole threshold, you go right back out. Okay, so when you start reusing strings, that's when you actually get to the quark gluon plasma phase of this, which actually gets you into this. Okay, so now we can try to answer our question. So we take one of these circles and we put a graviton on it, a low energy graviton. That's the lowest energy state you could put on it. And it's a superposition of being on all these circles, right? So I wrote plus this, plus this. I'm not doing it properly. There's a 1 by n root n, the n of these guys. So some amplitude to be on the first copy, some to the second copy, because it's a symmetric orbifold. So I'm just being a little precise about it. And then that describes a graviton sitting at the bottom of the throat in the bulk, which basically represents my girl drinking coffee at the center of ADS CFT. Okay, now you can see what happens. As I start sending in my gravitons, more and more of those circles start getting occupied, and the circles on which, so the graviton may spread over to a circle which was already occupied, then I lose that guy. And if I haven't lost that guy is still there. So at this stage, there are 4 circles. Plus dot 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 means it could be on this circle, the graviton, or on this circle, or this circle, or this circle. There are only 4 of them left. So I have only an amplitude 4 over root n left at this stage, when I had an amplitude 1 by n, like n over root n in this case. So I'm slowly losing probability from the side of having the simple graviton. And if I actually get absorbed into this mess, I've got absorbed into whatever is my virtual fuzzball at this time. So I'm being very rough about it because I don't have much time, but you can see this is the picture. If you just go and follow this picture of what you have, you can sort of see that what's happening on this side is like this guy slowly fading away in whatever we said was like the vanishing Cheshire cat. Okay, so this is a summary of what I just said, and I'll just put up my conclusion part, that if you have a picture like this part is the fuzzball, this part is the girl drinking coffee, and then what's really happening is that the inside region, what we think about, is actually being describing these strands, And what we have is the other description, we just have a fuzzball seen in the Schwarzschild frame, that's actually describing these strands. And because the full state is a superposition of something on these strands and something on these strands, it's just like alpha decay. If part of the wave function is there, part of the wave function is here, you can't represent all by one space-time. There's some description which has to show you what one piece is doing, some description has to show you what the other piece is doing, but the inside piece is slowly fading away like the Cheshire cat, and when you put all that together, we can talk about it more slowly, but I call it Schrodinger cat because it's in two pieces, but it's more like a Cheshire cat because it's really disappearing, and when you put that into account, you can sort of explain what the inside of the black hole really meant. Since I'm out of time, let me just, can I take 2 minutes? 2 minutes, okay. I'll just put the lesson you want to extract from this and then I'll stop. So the real question you want to ask is, can you ever get into a situation where the vacuum gravity equations hold? Like, so you say, I don't want any matter, let's put no matter, can we get these equations? But you can't really, because the vacuum fluctuations, the quantum fields will typically give you a stress tensor. For example, in the black hole background, if you choose the Unruh vacuum, then you get stress tensor at infinity from the radiation. It creates particles. If you choose a Boole vacuum, creates no particles, but itself has a negative energy density. So some of the quantum fields are such that if you try to make the stress tensor 0 here, it becomes non-zero somewhere else. Just a pain. But in 2D CFT, for example, the stress tensor trace is always given by the curvature scalar. So you can change t plus plus or t minus minus or t plus minus, but the trace together will remain always the same, right? So the t plus minus will change. So in a curved manifold, you don't have a choice. You'll always typically have some non-vanishing energy somewhere. And so we want to see what the intuition is. Roughly, if you want to minimize the energy which you're getting from all these quantum fluctuations, every wave function should have its optimal spread. Like if this is the potential, this wave function has the optimal spread to be the ground state. If you squeeze the wave function too much, so it doesn't have any fluctuations, you can see I made it very narrow so it doesn't have all the fluctuations, the energy goes up. If you spread it too much or too less, energy goes up. We know that from the quantum mechanics courses we all teach. So to get the closest approximate to the Einstein's equations, take the quantum state to have a spread which is as close to the optimal at all times. So all that of course we all know, but now everything that you want to know is in this picture. Here is the potential for various configurations, and if you have a star, this is the classical star configurations. These are the small fluctuations around there, semi-classical ones which we all know. But if you go far enough away, for the same radius, you can also tunnel into fuzzballs of that radius. But fuzzballs of that radius are black holes of that radius, and they are very heavy, so they have a high energy, but there are a lot of them, so they are here. But it's still high up there, so this guy won't tunnel there, but there's a small tail of the wave function in those fuzzballs. Does that look good to everybody? Because there has to be a tail. And that's the tail we have to think about, because even though right now the tail is small, when I make the star more dense, like let's say almost close to the black hole radius, then it can tunnel into fuzzballs of the same radius. They're again heavier than this guy, because this is slightly, it's a black hole, but only a little bit heavier, so the potential is not that high up there. And so if the potential is not that high, you can see the wave function spreads more, there's more support in the fuzzballs. Remember, there are a lot of fuzzballs there, so there's a lot of support there. The support in that direction is increasing. And if you actually try to make something which is inside its horizon radius, you find this situation and the wave function actually spreads as an oscillatory wave function because it can spread over all this space, and that's the time you have to spread into fuzzballs. And so this kind of thing I would say happens whenever you get into the situation where gravity was new. The tail of the wave function, you have to always think about it, because that's the tail which comes out and then stops being a tail. It actually becomes the oscillatory wave function. If you'd forgotten about those vacuum fluctuations, you'd always be puzzled, just like if Hawking didn't know about virtual fluctuations, he couldn't find the pairs that he finally found. And so the important thing is, if you try to have a low potential like I had in the last slide, but you choose a wave function which is so steep that doesn't spread all over, you can always choose that wave function, but then the energy will be too high. We already know the same kind of lesson from NS1P, a very simple case of two-charge solutions, that we have a certain minimum spread for the oscillating NS1. If we try to make the NS1 even more confined, what happens is the wave function becomes too narrowly confined and the energy goes up, and that's why there are no throats deeper than a certain amount. So in very simple cases, we know the analogous story. And so this is my last slide then. If we don't worry about these virtual fluctuations, we get into the situation where we have the information puzzle, but that's because we have, if we realize the wave function can't be squeezed to not spread over the fuzzballs, the energy of this guy goes too high, it is no longer m. So there's nothing like this. The energy would be wrong if you try to squeeze the wave function to this configuration. If you spread over these configurations, only then the mass can be m. The same thing resolves other puzzles. If you say that two entangled CFTs are dual to one, the eternal black hole, this also has horizons. But in fact, you find that the energy of the virtual fluctuations, if you squeeze it down to the state, makes the mass more than m. So you can't have that, and there are contradictions for this which you can show as we did in this paper. But the real thing would just be it breaks up into two fuzzballs, and you can never get this wormhole here. Same thing resolves the bag of gold problem, because if you don't have a horizon, only then you can get away from it. Otherwise, this is a very robust problem. And then, as we said in the beginning, it's possible that this resolves issues in cosmology like Hubble tertiary dark energy, but those are only guesses. This much we can do a lot about, because we also have the dual CFT and we can see where we are going. These are conjectures, but they certainly look interesting. I'll stop there.
Okay, thank you.
Maybe a very naive question, but for the infall time for, if you have a fuzzball and it's very like a black hole, there is still a crustal time, and there's something that looks like the crustal time that it presumably then cuts off at the surface of the fuzzball. But so is there any physics in this crustal time that you want to extract, or is it, are you just going to say the only time is the Schwarzschild time and that works everywhere and we're done?
So that particular one, I still want to come back and think about more. So I'm not answering that. So what we've done here is a part of the same question, right? If you start with, this is the way Emil once asked me this question not so long ago. It's sort of the same question, like if you're already sitting at r equal to 0 and you send the shell in to make the fuzzball, this shell will take the time of the order of whatever 3 hours to get here, right? And so you could ask whether this person has a life for those 3 hours, because the fuzzballs have sort of formed, they've already reached the horizon at this scale. And so the meaning of this time is what we were trying to explain. And so at least that you can see that because the wave function is split into two parts like a Schrodinger cat, you do need two different descriptions to explain those two pieces. And there's no point in saying that in this description, what is this time doing, or this description, what is this time doing. They're actually two different dynamics, and it's just like superposition. That's all that seems to be easily accessible from what the CFT has done. If you already had a fuzzball, throw something more on it, it's a little bit more messy. I do have some guesses as to where it goes, but it's more difficult to explain. So let's do it privately. Okay. Yeah. I have thought about it, so I do want to chat about it.
So, but it does seem like you're, in this sort of picture, you're imagining some sort of causal structure which is different than the naive effective bulk causal structure. Because there's some kind of clock in which this redistribution of probability density is taking place, right? You're saying probability density is fading away in the middle, it's building up somewhere else.
Yeah.
But there's some kind of quantum coherence
that
you're imagining, right, that allows this to happen in some kind of quantum coherent way. So at some level, it sounds like you're replacing the bulk causal structure with something else. And I'm wondering what that something else is.
So definitely I'm replacing it. So let's see, to get a better idea of this, let's go back to the bubble of nothing and keeping a quantum in the middle and waiting for the bubble to create. It's almost the same problem. And that we can imagine because we can almost do the calculation, right? We know the instanton, we know the path, and we can have a quantum, we can just modify the path to take into account the quantum. So in that case, what would one say? You can write the entire space-time diagram for the bubble of nothing tunneling. But really there's no space-time diagram for the part where you are under the barrier, right? You can just use one time and then just say you're under the potential for some time. You don't always have to be on shell, just a wave function tunneling. We do that even for alpha decay. You're just under the barrier. So you're looking at wave functions, but the wave functions are exponentially decaying in some region and then come out in some region. So let's just keep one time and study everything. And so if I just keep one time and study everything, it's just that the amplitude decreasing for the quanta in the middle and showing up in the bubble at later time. So at least completely clear what we are doing. We can do it in a computer. And now the point is there some way to describe the life of the inside guy just by itself without noticing the fact that his probability is decreasing? He's slowly fading away, but we don't want to see that his probability is decreasing. We just want to say what his behavior is for the part of the wave function which is there. Just like in alpha decay, I just want to keep it bouncing back and forth without keeping into account the fact that it actually may not be there after some time. To describe that, you have to create an artificial geometry which just encodes that behavior. It's just a tool. And so the point is, if you ever try to join the description which describes this business with the description of this business into one common space-time, it's not correct anyway. Because there are two parts of a wave function. It's like you had a Schrodinger cat half dead and half alive, and you want to put the Schrodinger cat into one common description, and you are wondering, like, how do I fuse it? So You can't really put them together into one Penrose diagram. I can draw you the Penrose diagram which corresponds to this branch of the wave function, and that just corresponds to this guy coming here and becoming a star. Okay, so we've all drawn that, I can draw that again, right? And if I want to draw the Penrose diagram which corresponds to this part of the wave function, then I can just focus on this part of the trajectory, or maybe right, this guy sitting at the origin, on this part of the trajectory, and this is all correct. And the point that these times can't be accessed from these times, that's an artifact of this picture. And I think that's what you were complaining about. Should I join the times here elegantly onto the times here to say that there's a light cone structure which prevents this time from going here and so on? I think that's where the troubles come. This total diagram doesn't make sense because you're putting two different animals together and trying to join them into one space-time picture, and there is no such picture. So I'm agreeing with you that you shouldn't put them into one causal picture, but if you're still faced with the question, if I'm falling in, I just don't even notice anything happening on the horizon. There must be some reality to this existence, or if you like, there must be some reality to this existence. I mean, this and this are two limits of the same question, right? It's all the inside of the stars. You want to describe all of this. Normally, this is called the experience of the infalling observer. This is the experience of the observer sitting at the origin, like this one. You can choose either. There are two limits. So I've just taken this one. For this one, anything you want to ask, I think we can now answer. And it's just that it's a different reality. Don't join together into one picture. But it's still true that this picture will describe the dynamics, as you can see from here. These strings are not affected by this. They do exactly what they were doing by themselves, like the particles just keep going round and round on those strings. It's just that the probability on this kind of excitation is just diminishing. So that you can't actually see. You have to renormalize that. You just see it, just like in alpha decay.
I had some comments. So my understanding of the way this quantum tunneling happens is that there's no more shell once you cross the horizon, because you have so many available end states for the situation inside the horizon. So the question is, you can ask, okay, what doesn't the person in the middle, tunnel into chocolate in empty space? The reason is, okay, two reasons. First of all, the entropy of chocolate is very small. Second one, the tunneling probability is very small. But when the shell goes and crosses the horizon, there's an available number of tunneling endpoints available for the person inside to tunnel. And what will happen is that, the person and the shell will just tunnel into some horrible mess. It doesn't need to be, I don't think there will be any notion of locality between the person inside and the shell. Whatever, 180 hours, I don't think that you'll have space-time even for these hours. The moment the shell is at the horizon, it discovers, hey, I can tunnel into all these things, it will tunnel. So once it tunnels, there's no more causality, there's no more space-time, there's nothing, including the lady in between. The whole space-time inside is just gone.
So it's actually, part of that is true. The whole space-time inside is done, that happens in a bubble of nothing, it's gone, right? But there is one very interesting...
There's a timing for that. I think the timing is, this happens once you cross the horizon. I don't think there's any more time. You don't wait until the shell goes. You have 180 hours from the moment when the shell goes until it hits the lady. You don't wait this 180 hours.
So there's actually, I think, one very strong causality constraint in tunneling in gravity, okay? And I have to be very careful with that, because that gives me a lot of trouble in coming to this final picture. And I was just very happy that constraint fits. So look at the following situation. Take the Witten bubble of nothing thing, but the compact dimension is 1 meter big. So the tunneling probability is very low now, right? So the universe will be stable for 1 million years. Now let's send in a scalar wave from infinity, which is a theta function, where the size of the circle is made small. You can make a wave, right? So as a wave comes in at the speed of light, the size of the circle becomes small. So it's leaving a small circle behind it. If the circle becomes small, let's say 10 Planck lengths, it will tunnel in 10 Planck times, 100 Planck times, 10 square, okay? Good, so let's ask the question. I'm sitting in this room, right now my tunneling time is the age of the universe. I'm happy I will reach the end of this seminar without dying. But now somebody has sent that shell, and that shell reaches the edge of this campus, where the circle has become very small, right now. Will I tunnel right now? In the next 10 to the 20 Planck times, will I immediately go there? Or only when that shell comes up to me, I can go there? Or you're saying no? So good. So that I have to wait for light to go at least from me to the place where the where the circle has become small before I can take advantage of the fact that tunneling is now cheap. That constraint is very important. The tunneling does have a causality built in. Like for example, even when you do bubble nucleation in cosmology, the bubble expands at a speed less than the speed of light, both on the inside metric and in the outside metric. So nobody has ever been able to violate a certain causality constraint in quantum tunneling in gravity. It always has a speed of light constraint in it. It's true for the bubble of nothing, it's true for bubble nucleation, And you have to be very careful that in all these pictures you have to maintain that. So I didn't give too many details here, but as this guy comes in more and more, it's easier and easier to tunnel because you still need to go from this time to this time. You need time to go from here to here. And that becomes easier here and here because the moment you fill more of these strings, it's more easy for you to just wallop the next string off, you know, because you don't just want to eat them. So you got to see that all these qualitative pictures are also fitting. You know, as you fill up more strings, it's easier to eat up the next string because the more guys eating up this string. So all the picture has to fit. And if something doesn't fit the causality, it's not true. The picture won't be good.
So, well, two versions, probably the same question. First of all, fuzzballs, you know, I used to sort of think of them in some sense as just being, from the point of view of the information problem, just no different from a neutron star in some sense. But now you're drawing a strong difference, which is that somehow the fuzzball is intrinsically quantum, is very, very important to the description of the states inside it. So, but yet I was resisting what Joseph was saying, that there's an instant change, because I still think the infall time probably should have some meaning, and it must be along the lines of the time scale upon which it takes for you to cease to be classical and dissolve into the quantum system. That should be roughly like the light crossing time of the black hole.
So let me say both yes and no. Okay, good.
So the two questions, one of which is, you know, to what extent is the interior of a fuzzball like a neutron star, not terribly mysterious in that respect? And then the second one is there a meaning to the infall time, and is it just simply the decoherence time into the quantum system?
Yeah, so again, as I said, I haven't really answered the question of the fuzzball formation because I was focusing on this part of the trajectory here. Like I'm just giving a model for what happens here and not for a model of what happens here. So, okay, so I'm already saying that I'm not answering that question. But it's not important in what we have done here for one part of this that the fuzzballs are very quantum, because what happens here, the fact we are saying is just Schrodinger cat or the Cheshire cat, some part of the wave function is vanishing, appearing somewhere, is also true for the bubble of nothing. So the main point I made here is also true for bubble of nothing, which is quantum in the sense that tunneling is quantum, right? And the only extra thing we've used about fuzzballs is that tunneling probability is low, but it's enhanced by the entropy, which is a bubble of nothing and no entropy, so there's nothing to do there. So the fact there's so many states, that's crucial, that's really black hole physics. But otherwise the quantum nature hasn't been used any more than in the bubble of nothing doing the same thing. But time-wise, it is an important issue because, as I was saying before, you can't suddenly tunnel from a place to another place just because you can go there. The wave function takes time to spread because the wave functional always evolves in a causal fashion. If I deform the wave functional here, it won't suddenly change at the edge of campus. It will flow and flow like a bunch of water and then reach the edge of campus. So that's why all these time scales are coming, and then you have to try to match the fact that here, as you go further and further down, eating more and more strands, the progress becomes even faster. That has to match onto the fact that things can tunnel more and more easily as you get closer here. And all that has to fit, otherwise if even one thing doesn't fit, it's gone. So we're still trying to fit in all the numbers, but so far it looks okay.
Okay, so maybe the last question.
A paper that might be useful for the interior time is by Maldacena and Greenberg, who considered a theory of higher curvature gravity with a massive infall layer. And they argued that they can extract the time up until hitting the singularity from a one-point function on the CFT in a thermal state. So it could be a useful
Let me take
paper.
the reference from you. I would love to see
Absolutely.
that, I think I've seen that before, but I may not have. So please tell me,
Okay, so maybe this is a good point to stop. And since this is the last talk, let me take the occasion to thank the organizer, Josip and Nick.